So let's start with administration. First and foremost, things that I apparently did not include in my email was that next Monday is actually Labor Day. And so we will not have class on Labor Day because that's a energy saving holiday at the, at the university. So we will not have class on Monday. So I have extended the Module 2 homework to Wednesday at midnight. We should get all the way through Module 2 in the next 3 lectures, and so that should give you plenty of time to start the homework and then finish it when we have it. The last module in Module 2 is actually IR spectroscopy. And so I like to do IR really up front to, number one, show you the differences between the functional groups and that they are real. They're not just this imaginary thing, and we can prove that by just looking at the IR spectroscopy. Okay, so in addition to that, we have I have uploaded to Canvas 3 new things. One is a tentative schedule for lectures, homework, and exams. And I'm gonna go ahead and share my screen and show you what that looks like. It's on Canvas for easy access. It's right up top under Files. So tentatively, I have the class days, and notice, for example, we have Monday's a holiday. So I actually have NA, no, not applicable there, which makes our Module 2 homework, due on the 9th. We're gonna start, we'll probably start Module 3 this week, and on Friday, we're gonna have our first group activity, okay? It's basically nomenclature of all the different rules we use together, and we're gonna use that. And so it'll kind of solidify all the different rules of nomenclature. The key of nomenclature, as you'll find out later today, is follow the steps in order. If we follow the steps in order, nomenclature is not hard. It's just oops, I gotta let somebody in. It's just following the pattern and getting that to go correctly. Okay, so let me go ahead and put my screen over here since I'm already sharing. Okay, so in addition to this schedule right here that we have, I also uploaded there is kind of a cheat sheet for nomenclature. And so what it is it's this right here. It's taken from a couple different books, but it is the cheat sheet. It gives you all the functional groups, kind of the general classes, but then it goes through the rules in order, okay? The basic rules, okay? And rule 1 is technically rule 0. You look for the functional group, and we'll talk about that today, but then all the other rules follow in order. And we go into the concept of substituent, prefix, infix, suffix. So this kind of gets it all into one place in all the different classifications thereof and things that you will need to know. And then on the last page is what we call the priority page. And basically, the substituent with the highest, the functional group with the highest priority is what we will be naming the compound for, okay? So, yes, the group activity is an in-class activity. We're all gonna get in and break out into breakout rooms and try our best at figuring out all the names. So we'll want to, number 1, learn all these functional groups. And if you look on this table in particular, there is a generalized structure, and you can use those for, and you can use those to make flashcards if that's how you would learn better or whatever, but it's a generalized structure. So the idea is the part that's not the R group is the key part of it. So we'll talk about that a little bit more as well. So that's also on Canvas, and so that you can use that as a good way to help you when you're doing your homework, but you want to kind of not rely on it too much because you want to start learning these things. You want to use it as the basis to be able to learn all of these things. Once we learn all these functional groups, we're going to go every single chapter, we're going to learn something new about that functional group and learn how to make it and going back and forth. So instead of spending our time learning about, what an alcohol is in each chapter, we're just going to learn about the reactions it does. So we're going to spend this chapter learning about our functional groups. And then the last thing I uploaded to Tracks on Canvas is this one right here. And this actually comes out of the reading assignment. And so it's just basically a copy and paste from the reading assignment, but it gives you an idea of all the different functional groups we will be looking at in both semesters. We're going to get all the way through to some of the carbonyl compounds this semester, but it'll give you all the functional groups that we'll actually finally do by the end of the whole semester. And so it's a good idea to, you know, kind of get very familiar with these functional groups and what they look like in general. Okay, so that is my administration. Nick had something he wanted to say about SI and ACS meeting. So I'm going to go ahead and let Nick share his screen or make him.
Oh, yes, thank you. So SI, first thing, turnout yesterday at our SI meeting was quite poor. We had 2 people show up, but if you ask those 2 people, they actually, you know, probably preferred it that way. However, I would like to make sure that we have a full capacity for our SI sessions. So if you haven't been assigned a session, please shoot me an email. I'll send it in the chat again. And if you're having any issues finding links or anything, shoot me an email. I respond pretty quickly, but let's try to get attendance for SI sessions up because, you know, they are part of your overall grade and they are very helpful. So that's my thing for SI. And as for ACS, ACS is the American Chemical Society. There's a student chapter here at our university. I'm the vice president for this organization, and our first meeting is tomorrow at 5:30 on Zoom. If you'd like to attend, an email is down here at the bottom. If you send an email there, you'll get a link and get put on our Canvas site. So if you don't have anything going on tomorrow at 5:30, I strongly recommend you attend. It's going to be a lot of fun. So that's all I have to say about that. I think I saw something in the chat.
Yeah, when do they know their times and logins?
What time and day mine was. So you should have gotten a email telling you what day and time you received you're supposed to be attending for your SI sessions. If you, let me make that full screen. If you can't find that email for whatever reason, shoot me an email. And then, was there another question?
Similar question.
When they are scheduled. So there is a flyer on the files tab, if I'm not wrong, files on the Canvas site. Yeah. It says SI session flyer. It's right there. It has all the links. However, you have been assigned one SI session in particular, so please try to attend that one every week. But if you found out that you missed it, feel free to attend the remaining sessions. There's one tomorrow at 1 p.m. and then on Friday, I think it's at 9, right before class. So like I said, shoot me an email, I'll put my email in the chat, and I guess we can get started with lecture. Thank you.
So for the SI participation grade, the idea is you get 100% of the SI participation grade if you attend 10 of the SI sessions before November 10th. So that gives you an opportunity to miss 1 or 2 and still get full credit. You know, try to get this as part of your regular schedule and start attending, and, you know, be prepared, ask questions. Nick has a prepared class structure, and it usually kind of feathers in with what we're doing in class. So it's a good opportunity to get that extra one-on-one attention. Okay, so
I have a question about that. I have a question about that, SI.
Yes.
Because I kind of joined a little late. I haven't seen anywhere where the SI sessions are going to, like, when are they? Because we all completed that survey, you know. I haven't checked my email and stuff. I don't know when exactly those are starting.
Okay, they started on Monday.
Okay.
We've had one session on Monday, one session on Tuesday, and then 2 more Thursday and Friday. If you haven't gotten any email, again, shoot me an email, but there is a flyer on the Canvas site that has all the SI session times. So just shoot me an email and we can figure it out outside of the class.
Okay, so I'll make sure to do that. And there still are some this week, you said?
Yes,
like
so if you were to miss one, you can still get points by attending another session. And you can get credit for up to 2 sessions a week. So you can't like knock out all your SI session attendance points in like 2 weeks. You can only get a max of 2.
Yeah.
So lots of information, pretty confusing. There's a lot of information on the syllabus that Dr. Irving has. And again, I'm pretty available on email all day. So
yeah.
Thank you.
No problem.
And I just looked at the flyer, his email's on that flyer. So go ahead and get that flyer downloaded. And then once you email and figure out which your time and day are, go ahead and write that down as your assigned day. And so kind of work that into your schedule.
Thank you.
Okay, technically I do not have office hours. However, because when I did have office hours, nobody showed up. So just email me if you want to have an office hours, and I'll set up a private Zoom lesson and we'll do that. Okay. Okay, if there are no other questions, I think that answered everything in the Zoom chat. We got about 30 of us here and we're recording, so it's time to move on to our slides. Module 2. So I'm going to go ahead and share my screen. Let's see what we look like over here. Okay, so Module 2. The first half of Module 2, actually the first 2/3 of Module 2, is nomenclature. The systematic way in which we're going to name chemical structures. The second half of this, Module 2.2, is IR. Or infrared spectroscopy. And so what we're going to learn from infrared spectroscopy is, number one, each of the functional groups actually shows up in a different place in our IR spectroscopy. So it gives you an idea of, ooh, these are the different functional groups. And because of those different bonds that we have in those different functional groups, we're going to see different absorptions in the IR. And so by feathering nomenclature, functional groups, and IR together, we're going to get a full understanding of all the different kinds of bonds we're going to see. And then as we move on with other chapters, we're going to see how we can make those different functional groups and interconvert those functional groups. Okay, so the general idea is that we are going to look first at hydrocarbons, which are things that just are carbon and hydrogen, to give us the basic understanding of the skeletal structure of organic compounds. Once we do that, then we're going to start adding other atoms to it that give us functional groups. And so those functional groups tend to be the ones that do the reactivity, tend to have the ones that are going to react first where other groups might not. And so different functional groups have different reactivity and they are sensitive to different chemicals. And so we'll start to see that in the follow-on chapters as we do individual systems. Now, what we're going to also think about is we have what we call the IUPAC. The International Union of Pure and Applied Chemistry, set up a series of rules, and when used correctly and in order, that you will have an unambiguous identifier for each and every molecule. Basically, if I use those rules and write out a huge long name for a chemical, I could give that huge long name to you and you could draw the structure. Okay, so that's what we're looking for in this nomenclature. Is it needs to be unambiguous. It needs to be precise enough that we can actually just hand each other pictures and write out the name, or hand each other names and write out the picture. That's the entire purpose of the codified way in which we do nomenclature. Okay, so I used to just say, oh, well, let's start with hydrocarbons. Well, no, I want to start with understanding the different parts of the name, okay? So chemical names get really, really long, okay? So we have to start thinking about which part of the name tells us what thing, okay? So I want to break each chemical name down into 3 things. One is called the prefix, okay? That's the beginning of the word. It tells all lower priority groups attached to the parent and the number of carbons in the parent. And I'll define parent a little bit, okay? So that's telling us everything attached to it and what that main chain is, okay? Now, the infix tells us the nature of the carbon-carbon bonds, okay? So if we only have single carbon-carbon bonds, that's gonna give us one name. If we have a carbon-carbon double bond, that's gonna give us a different infix. And if we have a carbon-carbon triple bond, that's gonna give us a different infix. And we can even have mixtures of those, and we have a rule for doing that as well, okay? Then the last part of the name, the thing tacked onto the end, tells us the class of compound, or basically the functional group. And the way we tell which is the functional group is by its priority of precedent. And so some things are more important because of their reactivity or their structure, and some things are less important. So we take the highest or most important functional group and make that the name of the compound, and everything else goes in the prefix. All the other groups are in the prefix, okay? So you can think of it as the prefix also has the substituents and the number of carbons. The infix tells you whether you have carbon-carbon single bonds, carbon-carbon double bonds, carbon-carbon triple bonds, and the suffix tells you which functional group it is. Okay. So that leads us to that sheet that I have online. I'm not going to go through all these right now. We're going to go through them as we continue on. But we have, number one, you need to get familiar with all of these functional groups, be able to identify them as the different groups they are based on which atoms are bonded in which order. And then on the other side of this is what we have is the priority list here. This priority list is very similar to the priority list that's on the Canvas site. In fact, it should be identical. So, but I added a couple things. For example, things when we have benzenes, I added another column here. So we don't really have to worry about those benzene names right away. That's going to be in the second semester of organic. But if you take that with you forward into your second semester organic, you'll have a jump ahead in looking at how we can name those benzene groups. Okay, so I'll start with some of these, and then we're going to continue on, and I'm going to look at each one of these functional groups independently as we go forward. Okay, so the first and simplest thing to start with is what we call hydrocarbons. Hydrocarbons are only made of hydrogen and carbon, and then that's it, no other atoms. In the case of adding other atoms that are other than hydrogen or carbon, we call those heteroatoms, meaning other than carbon and hydrogen. So occasionally I'll say, then we throw in a heteroatom. That means throwing in a nitrogen or an oxygen or something else, okay? So, but if I just say hydrocarbon, that means only carbons and hydrogens, okay? So the simplest of these are what we call aliphatic systems. And in aliphatic systems, they are made in which they react a certain way. They can have single carbon-carbon bonds, they can have double carbon-carbon bonds, and they can have triple carbon-carbon bonds, but they don't have that different reactivity we get when we have what we call an aromatic compound. An aromatic compound actually has a certain structure such that it has this really stable ring structure, okay? Most aromatics are rings, and they have this really stable structure, and it makes them react differently. So our two major classes are aliphatic, those that don't have aromatic rings, and those that are aromatic and do have aromatic. Okay. So the simplest of the hydrocarbons is what we call the alkanes. See the A-N-E here? This is important. This is the infix right here that identifies the idea that all we have is carbon and hydrogen, and we only have sigma bonds, or we only have single bonds between the carbons, okay? So we can imagine that to be the simplest one. All the carbons are sp3 hybridized. So all sp3 hybridized. So they are all bonded to 4 other things, okay? And so the generalized formula for that, if we have that, is the Cn, meaning that however many numbers of carbons you have, you're going to have 2 times that number plus 2 to make that general formula, okay? So if we have a 6 carbons, a C6, that means we're going to have 6 times 2, 12 plus 2 is 14. So that's the simplest system we can have as far as an alkane goes, okay? So alkanes only have single bonds, and they only have carbon and hydrogen, okay? And we name them by the number of carbons that they have in their chain. And then we add the suffix ane, because there is no other functional group. Okay, so it's an infix, and in this case, because there's no other functional group, it's also the suffix. Okay. Okay, so because we name the hydrocarbon based on the number of carbons in the parent chain, we have to have a systematic way of telling us the number of carbons and what that name would be. And so we have this is what we call the hydrocarbon longest continuous, I'm sorry, the hydrocarbon names are based on that number of carbons. So for example, if we only have one carbon in the chain, that's the simplest hydrocarbon we can make, and it starts with the parent name meth, okay? So not the stuff you buy on the street, this is different. This is a one carbon hydrocarbon chain, and because it can only be bonded to that, we have the ANE at the end. So that's telling you it only has carbon-carbon single bonds, and it has one carbon. So we have a nice systematic way of saying, if I say methane, you always think, oh, one carbon, 4 hydrogens, done. Okay, so as we get to more and more, we have to remember these different parent names. These are names you must know, and so it's good to put at least up to about 20 right here, and then we'll rarely use these, but up to 20 you need to know. So when we go to 2 carbons, that changes the meth to eth, and so we go from methane to ethane, okay? So eth is 2, prop is 3, so we have, you can almost think propeller, 3 propellers, prop, and so it'd be propane. 4 is bute, right here, and then it gets simpler because it follows the more classical Roman or Greek naming structure of penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. And then for the other carbons all the way up to 20, we put the un, meaning 1 decane, dodecane, meaning 2 decane, 3 decane, and so it's 1 plus 10, 2 plus 10, 3 plus 10, 4 plus 10, all the way up to icosa. And the icosane is the C20. That's the largest one you have to put into memory, okay? So if I said, oh, we have a carbon chain and its longest carbon chain is 11 carbons, then immediately you're going to say, okay, that's un decane, because we said that it was the longest chain has to have 11 carbons in it, and we only have these saturated hydrocarbons or these simple hydrocarbons with only carbon-carbon single bonds. Okay, questions about that? So this is how we named that longest chain. Okay, and so we always name it by this systematic method. Okay, so if you have just 20 carbons in a straight chain, good, you're done. You know it's 20 carbons, you know they're in a straight chain. However, the rule states that we have to have the longest continuous chain, okay, which means that you can have a chain of hydrocarbons and then have a branch coming off, okay? And we call these branched alkanes. So you might want to think of it as the longest carbon chain is the trunk of the tree. Oops, that's not a very contrasting color. There we go, the trunk of the tree. So that's the longest one. And then you have different substituents. You can have 1, 10, 20 substituents, depending on how long your chain is. And all of those little branches are what we call substituents, and they all have to be named as a prefix because they are a substituent to the parent chain. Okay, so let's look at some of those possibilities there. So substituents are anything that sticks off the main chain, okay? So in hydrocarbons, if we only have carbon and hydrogen, then they also must contain only carbon and hydrogen, okay? And they can either be branched, which means the stick coming off can be just a straight chain itself, but smaller, or it can be a straight chain that comes off and then itself breaks into another chain, okay? So we need to know whether that little branch coming off there has a branch to it or it does not. and that changes the name, even though it may have the same number of carbons. Okay, so let's look at some of those different groups. Okay. So if they're simple little chains, then we only have to name it for the number of carbons in that chain. But instead of having the A and E at the end, we put the YL on it so that we note that it is a substituent, okay? And look at the name up here, alkyl, okay? Which means it can be any hydrocarbon, but because it's not the parent chain, we have to do the YL, and it becomes an alkyl substituent. And so we want to add that name. So if we have one carbon, we look back at that table, one carbon is meth, so that becomes the methyl group. Okay. Two carbons, that's F, becomes the ethyl group. Okay. And if you had a straight chain of 4 carbons, that would be bute. That would turn into butyl group. Okay. So just as a side check, what is our parent hydrocarbon here? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbons in our main chain. And yes, that's right, nonane. So that would be our non is 9, and it's nonane because it's a hydrocarbon chain. And now we have 2 substituents on it, and we'll figure out how to number those substituents in a little bit. Okay, but these are linear or non-branched alkyl substituents. Okay, so what if it gets a little more complicated? Well, it's going to, and so we have rules for this. Okay, so when we think about a branched alkane, we have to think of it as a substituent, and we have to name that substituent correctly. So the carbon directly attached to the parent chain is assigned the number 1. It's most important because this one is always number 1 because it's the one that's coming off that parent chain. And remember, you're naming that compound for the parent chain, so you have to name the substituent for where that substituent attaches to the longest chain, okay? So now that we know that that's gonna be that, we have still our longest parent chain here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3. So this is now undecane because it's now 11 carbons long, but our side chain here has a total of 5 carbons, but the longest continuous chain in that means the substituent needs to be called 1, 2, 3, 4, butyl, right here. And we have to show where this other substituent is here. Okay, so we have some simple branch chains that actually have common names that we can use. Okay, and we'll look at those in a minute. Okay, now, also it's on the Canvas site in that nomenclature rules, the classification of carbon atoms. Okay, so the idea here is that number 1, it helps us identify, oh, I have a hand raised.
Yeah, I was just wondering what was the full name for the last example?
Oh, let's see. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's undecane, and it would be, let's see. I haven't got up to all those rules yet, so I didn't name it.
Oh, okay.
6, 7, 8, 9, 10, 11. So it's going to be something like 6 butyl 2-methyl undecane, but we don't have all the rules yet. So let's wait. Okay.
Okay, thank you.
Okay. So now that we have branching, right? We have these long straight chains, and we have branches, and we have a bunch of different ways to do it. We have to show that these different atoms, these different carbons have different a classification to them. And so when we look at a carbon that is only attached to one other carbon, okay. Now remember, when we drew those stick structures in module 1, if it has an end and an end, those are carbons, and the hydrogens are assumed, and that line is just that sigma bond between them. Don't forget that, okay? So if we only have one other carbon bonded to a carbon, that makes this carbon a primary carbon because it only has one other carbon attached to it. So what that also means is it has 3 hydrogens attached to it, okay? And so that gives you its type of reactivity, how it's going to bond and everything. It has to do with the idea that it has those 3 hydrogens and only 1 carbon. Okay. Now, if we have 2 carbons bonded to something, like in this case right here, so we have 1 on that side and 1 on that side, that becomes a secondary. So that's pretty simple to, understand. So we have 1 carbon is primary, 2 carbons secondary. So that makes our 3rd carbon here. If we add 3 carbons, 1, 2, 3, that makes it tertiary. And this last example here is 4, okay? So knowing that you have how many carbon substituents you have on there tells you the classification of carbons.
I have a question.
Yes.
How do you pronounce, is it quaternary?
Quaternary.
Quaternary, that's how you pronounce that. Cool.
Quaternary, yeah.
Thank you.
Primary, secondary, tertiary, and quaternary. On the East Coast, it's quaternary, but for us, it's quaternary.
Okay.
Okay, so that's going to help us identify some things about our branching on our substituents and our main chain as well. Okay, so like I said before, when we have these branches coming off, we have some common names because they are used so much, and it makes them very easy to identify quickly. I'm going to show you both the IUPAC name and the common name, and it's appropriate most of the time to use either one. You can use the common name if it's a substituent, okay? Or if it's a functional group, there are some common names we can use, and we name them slightly differently. But I want to show you each of these separately. So the methyl and ethyl are pretty easy because we only have one isomer of that, right? So methyl can only ever be methyl because there's only one carbon there as your side chain. Ethyl can only be ethyl because there's no way to branch that. There's no other isomer available to it. However, once we get to 3 carbons, we now can have 2 different isomers, okay? And so the different isomers we're going to look at are the straight chain isomer. So that's the one where it's just a long chain, almost like the parent chain, okay, with no branching. But then there's also the branched ones. And the more carbons we add, the more possible structures we can have, okay? So let me go ahead and talk through these first ones here. So when we name the straight chain substituents, all we look at is the number of carbons that are in that chain and add the YL, okay? So we have 3 carbons, prop-yl, 4 carbons, but-yl, 10 carbons, deca-yl, okay? So it's very nice and simple with the straight chains. However, now that we have the possibility of branching and isomers, we have to find a nice, clean way to name these, okay? So if we look at our first set of, our first isomer here, if we take that propyl group and instead of being that long straight chain, we just move a methyl group from one side to over here, we end up with this right here. The common name for it is isopropyl, okay? Because propyl is the straight chain. Well, this is an isomer of propyl, so it's the isopropyl, okay? And it's the simplest one. But the IUPAC name would be 1-methyl-ethyl because the longest chain is these 2 carbons here. And because this is where your parent is, this is going to be your number 1 carbon, that's going to be your number 2 carbon, and this methyl substituent is hanging off that. And so it's on the 1 carbon of the substituent, giving it the 1-methyl-ethyl as its name, okay? So a lot of times it's easier to just say isopropyl group, okay? And it's a very common group. We have things like isopropyl alcohol, which we'll talk about, and the isopropyl group if there's some other main chain, okay? So now if we, if we add a carbon, to our system, now we actually can have more than one isomer, okay? So here we only had the one branched isomer for propyl. When we go to butyl, we actually have several isomers possible. And we have one that looks a lot like the isopropyl group, which would have been here. And we've added one more carbon to it, and so it becomes the isobutyl group. Is there a question? Where did the ethyl come from? Did I already answer that question? Do you still, you mean on this section here? I have a question in the chat about, okay. That section, or did I answer your question? Okay, so.
Question?
Yes.
Should it? So you said there's a. If you're getting, based on what you said, what is it? The IUPAC, is that what it's called?
IUPAC is for short, yeah.
It sounds like it would just be better to memorize those names, because it seems like it would be like a way that you said it was a way that you can see any molecule and name them.
The IUPAC name is always right. Okay?
Yeah.
However, in shorthand, the names like isopropyl, isobutyl will come up a lot. So
Okay.
people will say, oh, this is isobutyl alcohol. It's like, okay, what was isobutyl again? So that's why we want to remember these common substituent names. Okay. Okay. But yes, IUPAC name is always right.
Okay, that makes sense. That's a really, really amazingly helpful thing to do, though. Have a system for any molecule.
Yeah, and there is actually molecules with page-long names, and if you start at the beginning and start putting everything together, you will get the right molecule at the end.
That makes sense, because we're talking about like 100 carbons for one of the, yeah. Okay.
Yeah, it's amazing. All right, but good point. Yeah, IUPAC's always right, but you need to know these because they're commonly used. Okay, so this kind of looks like this isopropyl group here, which is that little group there, and so but we add another carbon to it, and so it becomes the isobutyl group. Okay, so because we've added another carbon, we can actually move this methyl group around. If this methyl group was on the end of the chain, it would be that straight chain butyl group. By moving it over one carbon, that gives us the isobutyl group. Okay. Now, if we move it over one more carbon, so it's on the carbon next to where it's attached to the parent chain, that's now the sec-butyl group. Okay, because we've moved it one position to get to the isobutyl, we moved it a second position to get it to the sec-butyl. Okay. And so it looks a little different. It looks like you have this, the propyl chain with the methyl coming off in the 1 position. The isobutyl is the propyl chain with the methyl coming off in the 2 position. Okay. So the only other isomer available to us is to take this last methyl group and move it onto that number 1 carbon again. And so what we'll end up with is our parent is now only 2 carbons long, because it's our parent substituent is now only 2 carbons long. And we had to add those methyl groups in on that 1 carbon. So we call that tert butyl or tertiary butyl. What you can think about it is that gives you the carbon that is attaching to the parent chain is now a tertiary carbon before it attaches to the chain, because it has 3 groups already on it before it attaches to the chain. The sec-butyl was a secondary carbon before it attached to the parent chain. And so it is, that's one way to remember it. So in the T-butyl, tertiary butyl or T-butyl, it's 1,1-methyl ethyl is the IUPAC name. Okay, so are you starting to see the system here? And I know at least a way you can remember the different branched hydrocarbon common names. Okay. Okay, now let's do the last ones that we usually do. There's also one higher one called the neopentyl, but let's look at an isomers of the butyl. I'm sorry. These are the butyl. These are the pentyls. Okay. So now we go up from 4 carbons to 5 carbons, and we can still see some of those common names. Like, so again, we have this little structure here that looks like that isopropyl group. We call that isopentyl. And all we've done is taken that straight chain and moved it over one from the end. And so we have the 3-methylbutyl. Okay. Now, if we have a T-butyl group on that long chain with a total of 5 carbons, so this looks a lot like this T-butyl group down here, but we still have that extra carbon here, we call that neopentyl, okay? And it comes from the idea that a compound with 5 carbons like that is actually called neopentane. Okay. So these are the 2 major isomers of the pentyl group we need to go. You need to know the straight chain one is always pentyl. Moving one of those methyl groups from the end, one over, gives you the isopentyl because it's like the isobutyl and the isopropyl. And then the neopentyl is the one that's basically a star hanging off the chain. Okay. So that brings us to, now we need to link a few rules together to figure out exactly how to name that. And so now we're going to go back to the question I had before about what was that name, okay? Now we have enough rules that we can start to name these things. So the first rule is to identify the parent chain. Now, there's a sub-rule to that is what is the functional group? And because we don't have anything but hydrocarbons here, the hydrocarbon is the parent chain. So we need to identify the parent chain. The parent chain is the longest amount of carbons all in a row, okay? So once we've picked that, we need to identify the substituents, okay? And then we need to assign the location for each substituent, and then we need to name the compound, okay? And when we name the compound, we're gonna list the substituents in alphabetical order. Okay. So assigning the location is now what we need to figure out, okay? We know how to identify parents, we know how to identify substituents, now let's start assigning location, okay? So when we look at assigning locations, the rule is to try to have the lowest number of the locations for all of your substituents, okay? So, for example, right here, if we looked at this chain right here, and we saw that that was the longest continuous carbon chain, with a total of 6 carbons, but we still had 3 substituents on it. We need to find a location for all 3 of those substituents, okay? So we could number it from one side like this, 1, 2, 3, 4, 5, 6, and we've done nothing wrong so far. But now if we look at where the substituents are, our first substituent here is a methyl group on a 3 carbon. The second substituent is a methyl group on a 3 carbon. And the third substituent is the methyl group on the 5 carbon, okay? So that gives us an opportunity for 3, 3, 5. Okay. Are we right? I don't know. Let's number it from the other direction and see if we get a lower number, okay? So on the other side of this, we're numbering it from the other side. We're gonna number it from the side first, 1, 2, 3, 4, 5, 6. And when we start counting our first substituent, this is now on the 2 carbon, and this is on the 4 carbon, and this is on the 4 carbon, okay? Now, it's not the sum of the numbers. Don't try to get to, you know, the sum of the numbers. What we're looking for is the first substituent needs to be on the lowest number, okay? So if we look at this one, our first substituent is on a 3. If we look at this one, our first substituent is on a 2. That means we have to number from that side of the molecule, okay? So we have to number our first substituent 2 and our next 2 substituents on 4. Okay. So that's where we get the numbers. However, the next thing we need to add is if all the substituents are the same, we can just call them the same, but we have to put the number of things we have on there. So if it's just one substituent, it'd be the methyl substituent, okay? But if we have 2 methyl substituents and we've identified the locations, like the 2 and the 4, we can call it dimethyl, but we just have to identify where the numbers are. If we have 3, it's tri, 4, tetra, penta, and it goes up using those same rules that we, you know, that we go with the hexa, octanana, those. So That being said, we now have our parent chain numbered correctly, so our first substituent's on the lowest number. We have 3 equivalent substituents, so they can all be lumped together as trimethyl. So the correct name for this is actually the 2,4,4 trimethyl hexane. Okay. Longest chain, first substituent on the lowest number, and then identify where the substituents are. So the 2 is on the first one, 4,4 is where the last 2 are, trimethyl hexane. Okay. Now, what if they're not all the same? Well, we have a rule for that too. Okay. So once all the substituents have been identified and their proper location has been established, that means number, putting the first substituent on the lowest number, okay, and they're not the same, we start looking at them in alphabetical order. Okay. The prefix for numbers don't count, which means that if you had something that had an ethyl group, a methyl group, and a propyl group, propyl group, all on the same chain, you would put them in the order in which they are alphabetical. So E comes before and then MNOP, so M is next and propyl's next. So if you, then, well, let's change the last one to butyl. Okay, because that gives us butyl. Okay, which means the butyl is going to have to come first in the naming because it's alphabetically first. And we put the whatever number it is associated with that group here. Then we'll have the ethyl group and whatever number is associated with that there, and then whatever number associated with there. Okay. Now, to make sure we're correctly assigning our number to the substituent, we're going to put stuff like, let me rewrite these. The substituent where it is. So for example, 4-butyl hyphen 3-ethyl hyphen 6-methyl. Okay, so the number is identifying which of this hyphen is saying this substituent is on that 4-carbon. And then we now have a different substituent. This substituent is on the 3-carbon. We have a different substituent, and this substituent is on the 6-carbon. Okay. Now, if we're using a prefix that is already on the name, for example, we use the common name like isobutyl or tert-butyl, you don't ignore the iso and the neo, but you do ignore the second, the tert. And the way to remember that is if there's a hyphen in the prefix, it is not count in alphabetization. If it's attached to the name, you do count it. Okay, so these are a little bit rules, but they're all kind of codified here, and we're going to explore them a little bit more. Okay. All right. So now we know that we want to have it done so that we have the first substituent on the lowest number, okay? But what if you have the first substituent can be on the lowest number depending on which side you name it on? Now we have to do a more subtle rule. We want to get the lowest set of numbers, okay? So let's use this as an example here. So we're going to go back to that trimethyl group, but instead of having those 2 methyls on that 4-carbon, we're going to move them, okay? So we're going to move 1 to here and 1 to here. So in this case, we could number it from 1 to 6 on this side, and that's going to give a methyl group on a 2-carbon. If we named it 1 to 6 on the other direction, we still get a substituent on this 2-carbon, okay? So we have to look a little deeper. We have to look at the next substituent, okay, to try to get to that lowest number. Since either numbering system will give us a low number of 2, we have to go to the next substituent. So if we're going on this direction here, on this one right here, our next one's going to be on that 4-carbon, and that last one's going to be on our 5-carbon. Okay, what's it going to be on the, if we number it the other way? If we number it the other way, our next one's on the 3, okay? that 3 is lower than the 4, and this last one's on the 5. So that means we're going to have to number the first one doesn't change the number, doesn't change the name, but that second substituent does. This is the correct one because it has the lowest number. So when you have a choice between after your first number, it can be numbered either way, you have to look at the second one. And sometimes you even have to look at that third one to make sure that they're numbered correctly. Okay. So it's the same rule. We're just applying it for the next substituent because the first substituent was the same. Okay. Let's see, no questions, no hands up. All right. Okay, so now let's say we start to get a little more complicated. Okay, these are both compounds that are theoretically possible here. And let's say that we can count the same number of atoms in the parent chain. Okay, so note these are the exact same compound. So we're just looking at ways to name this exact same compound correctly. Okay, so when you have the possibility for having two different long chains, two of the different equally long chains, you always choose the one that has the greater number of substituents. Okay, now that tends to be because you'll actually get a more precise numbering. Okay, so in the case of this, if we started numbering, I'm just going to randomly number from one side to the other. 1, 2, 3, that would be 4 over here, so that can't be it. 5, 6, 7, 8, 9, 10, 9, 10, 9, 10. So we actually have 3 different ways we could get to that 10th carbon. Right? We only have 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 8, 9. There we go. Sorry, let me rewrite that. I skipped the 4. Okay. So what it's saying is that depending on which chain you go, this could be your 9 carbon. This could be your 9 carbon, this could be your 9 carbon, or this could be your 9 carbon. So what we have to do is we have to make a choice. And what we're making a choice is where we have the greatest number of substituents. So that could technically be this one or that one. We'll give a methyl substituent at the end. And so we'll end up with the choice that we'll have. This is our longest parent chain here. I'll highlight in red. And then we get to name it from here, okay? So if this is our longest parent chain, let's figure out which way to number it, okay? So since this one is substituent correct, I'm gonna try to leave it up there, okay? So if we were to number this from this side, we'd have 1, 2, 3. That would put our first substituent on the 3 carbon, okay? And this is 1, 2, 3. It would put our first substituent on the 2 carbon. So now we have to number from this side as 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we've correctly assigned our numbers, we've correctly assigned our parent chain, and now we just need to assign our groups. Now we have 2 methyl groups here, one here and one here, so we get to use a dimethyl. And we have 2 ethyl groups here, so we get to use a diethyl, okay? But ethyl comes before methyl, before we put the di on it, so the ethyl is gonna come first. Then the methyl is our only other substituent. It's going to come second. So let's identify where those different groups are. We have 1 ethyl on the 3 carbon. We have 1 ethyl on the 6 carbon. So we do 3, 6 dash diethyl. So we've assigned those 2 substituents because of their alphabetization first, dash, And then our methyl group is on the 2 carbon and on the 7 carbon here. So it's 2 comma 7 dash, there should be a dash there, dimethyl non-A. Okay. All right, so we've added a new rule of trying to get the greatest number of substituents available. Okay, parent chain, substituents, lowest number if you have to look to the second or third substituent, and now greatest number of substituents if you have a choice. Okay, where are we? Oh, we're right at time. Okay, so that's actually a great place to stop for. That's the numbering and labeling of substituents on linear hydrocarbons. And when we pick up on this on Friday, we will start with the cyclic systems. Okay, any questions before I stop recording? No hands up, no comments in the Zoom chat. Okay, so what I'm gonna do is I'm gonna go ahead and stop recording, and if you have somewhere to run off to, go ahead and run off.